Hello, everybody. Welcome to a new physics video. And today we're going to switch things up a bit. So far, up to this point, we've really focused on dynamics of singular objects. We've used Newton's second law, force equals mass times acceleration. For now, we're going to switch things up and we're going to start using conservation laws. There's a few different laws of conservation, one of them being conservation of momentum, which is what we're going to really focus in on today. So for this first problem, it is the first two problems that we're going to go through are just conceptual, and then we'll get into more mathematical problems. So I'll let you pause the video and read through this. But the important thing is that we have a 60-kilogram person standing on frictionless ice, and they throw a 2-kilogram ball. For system one, so just worrying about the ball, we ask, is the push from the person an external force? And the answer is yes. If we just worry about the person and the ball, or if we're just worrying about the ball, so not worried about the person at all, so the person, it doesn't matter what happens to them, then the push is an external force. In this case, the ball's momentum is not conserved. For it to be conserved, there has to be some momentum that happens in the opposite direction. So if the ball is here going in this direction, there's some object here going in the other direction. And then the mass times the velocity of each of these objects, say that this is 2, this is 1, has to be equal to each other. So the masses don't have to be equal and the velocities don't have to be equal, but these two equations have to be equal. For system 2, just worrying about the person, again, the push from the ball is now considered an external force, and momentum is not conserved. If we consider the person and the ball as a system together, so this whole thing, the push between them is an internal force. The person causes it. The person is going to move, in my diagram to the left a little bit, and the ball is going to move to the right. And the system's total horizontal momentum will be conserved in this case because we're looking at the whole system now. With conservation of momentum, it is really important to understand what the different types of collisions are. So in this case, we're going to consider a general collision between two objects, object one and object two. A perfectly inelastic collision, so problem one, is where the objects stick together. So let's say here's object one and here's object two. Object one is being thrown at object two, and then the system will then look like object one and object two stuck together, moving in the same direction that object one was initially moving. So inelastic is where they stick together and then they move with a single velocity. For part two, writing the general conservation equation for momentum you would use to solve a problem involving a perfectly inelastic collision. We have that the initial momentum of object one, I'm going to call it object A here, plus the initial momentum of object B has to equal the final momentum of A and B together, which is going to be the mass of A, little a, plus the mass of B times the velocity of A of the whole system together. A perfectly elastic collision, I'll draw down here. Let's say that this is like two billiard balls. They're very good examples of elastic collisions. Object A is moving towards object B and then bounces off of it, so that object A is now moving with some velocity over here, and object B is now over here. So forgive me if occasionally a little system notification pops up on the bottom. My GoodNotes seems to be downloading languages for one of their new updates. Anyways, This is a perfectly elastic collision where they bounce off of each other. In this case, since the objects aren't stuck together anymore, we can't just say that the final momentum is the masses together times the final velocity. So instead, we have to say that the initial momentum of A plus the initial momentum of B is equal to the final momentum of A plus the final momentum of B. So now we have our example problem. I'll let you pause the video and read through the whole thing so that you can understand what's happening. The key thing to realize is that Orion B, we have Orions A, B, and C. Orion B collides with Orion A inelastically along the vertical y-axis, and then Orion C collides with the combined system elastically and bounces off. And then there's some information in here about exactly how that happens. I'm going to go ahead and draw this. So we have, here's Orion A, which is initially at rest, and then Orion B comes up in this direction and collides with A elastically. So they stick together like that. Then we have Orion C comes in this direction and then bounces off at an angle of 30 degrees above the negative x-axis. So that is here. And then this is 30 degrees. So it kind of follows a path like this, where it's going, it collides with the system, and then it bounces off and goes off in that direction. And then it is returned to some holding orbit. So problem 3 wants us to calculate the velocity vector, the magnitude and direction of the combined Orion A-B system immediately after the perfect inelastic collision. So let's model that here. We have A and then B coming from below along this direction. If you look up, if you look here, you can pause and highlight anything important or write down anything important if you're following along. But we have that the velocity, the initial velocity of B is 0.45 meters per second. And then the masses of A and B respectively, let's find them. Mass of B is 300 kilograms and mass of A is 1200 kilograms. So this is 1200 kilograms, B was 300 kilograms. So this is an inelastic collision. So we use the equation that momentum initial of A plus initial momentum of B equals MA plus MB times the final momentum, or not the final momentum, sorry, the final velocity of the AB system. And then these are all vectors. So initial momentum of A, let's calculate that first. Well, we know that A starts at rest. So if we do mass times velocity, velocity is 0. So initial momentum of A is 0. Initial momentum of B is going to be 300 kilograms times 0.45 meters per second. So we have 300 times 0.45. And then we know that the combined masses is going to be 1200 plus 300. That is 1500 kilograms. Now we have a system that we can solve because we're trying to find this velocity vector after the perfectly inelastic collision. So we have 300, just use parentheses, times 0.45 equals 1500 times velocity of the combined system. So you can just do 300 times 0.45 divided by 1500, and you find that our velocity equals 0.09 meters per second. For part two of this question, it asks us to calculate the impulse delivered to the stationary Orion A module during this latching event. Impulse for A can be modeled as the change in momentum of A. So this is going to be the final momentum of A minus the initial momentum of A. Well, we know that initial momentum of A is 0. So it's just going to be the final momentum of A. So this is going to be the mass of A, 1200, times the velocity of A, which in our case is 0.09 meters per second. This is the velocity of the combined A-B system, which means that both A and B are moving with this velocity. And then this equals, if you plug it into the calculator, 108. And the units are, this is kilograms, and then this is velocity, so this is meters per second. We have 108 kilogram meters per second. Okay, now let's worry about Orion C. To remind you, we have here's A, which has a mass of 1200. Here's B, they're connected to each other right now. B has a mass of 300 kilograms. And then C is over here. It's going to do this, and then it's going to bounce off in that direction. And this angle is 30 degrees. And then let me real quick grab the info for C. It has a mass of 200 kilograms. It approaches at 0.5 meters per second. And it has a final velocity of 0.25 meters per second. So we have 0.5 meters per second. It weighs 200 kilograms, and then 0.25 meters per second. And then that's all the information we need for this. And a reminder that this collision is now going to be inelastic, or sorry, elastic. So first we want to calculate initial and final momentum just of Orion C in component form. And component form just means we're calculating the x and the y. So we want P initial for C. For Orion C is going to equal, I'm going to draw it as a vector with these open brackets. It's going to be 200 kilograms times 0.5 meters per second. Then that is the x. And then since it doesn't initially have any velocity in the y direction, the y component is just 0. And then the momentum final for C equals negative 200. So that's the mass. It's not negative mass, but we know that it's going in the negative direction here, so I'm including the negative sign now. Negative 200 times, and then this is going to be 0.25 cosine of 30. If we draw our triangle, here's our 0.25. This is 30. Let me zoom in here. So this is 0.25 cosine of 30. And then this one over here is 0.25 sine of 30. And then these are the velocity vectors in the x and y direction, respectively. So here's the x direction. And then the y direction is going to be positive. If you notice that this vector here is pointing up. So positive 200 times 0.25 sine of 30. And then the, let's calculate that out first. So this is going to equal, let's see, plug it in the calculator, we get negative 43.3 and 25. And then this top one, 200 times 0.5, that one's just going to be 100. With momentum, the momentum in the, well, we're asked to calculate the, well, there, we just calculated the initial and final momentum. So that was part one. Now we want to calculate the change in momentum of Orion C in component form. So this is going to be delta of momentum. And this is just going to be the difference between the initial momentum and the final momentums. So for the first one in component form, we have 100 and then negative 43.3. So if we do negative 43.3 minus 100, we get that it is negative 143.3. And reason that I'm saying that this is negative is initially, if you think about it, it has a momentum of 100 going to the right, and then it finishes with a momentum of 43.3 going to the left. That means that it needs to change enough momentum to switch it all the way around and make it go to the left. So it's negative. And then the y direction is much easier. We start out at 0 and we end up at 25. The difference between that is just going to be 25. The next part wants us to calculate the total impulse delivered to Orion C during the rebound. Total impulse is just the change in momentum. So this is going to be, since this is in component form, we want the magnitude. This is just going to be the square root of each component squared added together. So we have negative 143.3 squared plus 25 squared, and take the square root of that. If you put that into the calculator, you get that the impulse or the change in momentum is 145.46. The last question asks us to do the average force exerted on Orion C. Average force in regards to impulse is given by the impulse divided by delta t, where delta t is how long uh, the collision lasts. So in this case, our delta t was given, the impact lasts 0.05 seconds. So plugging that into this equation, we have 145.46 divided by, I believe it's 0.05. Yes. If you plug this into the calculator, you get 2,909.2 newtons is the average force applied to Orion C. Finally now, the last problem, we're going to look at the whole system through these series of questions. Question 1 asks what the impulse delivered to the Orion A-B system by Orion C. Well, impulse on AB is just going to be negative the impulse on C. In component form, we had that the impulse, which is the change in momentum here, is negative 143.3 and 25. So this is just going to be positive 143.3 and then negative 25. Calculate the final, question 2 now, calculate the final linear velocity of the system center of mass in component form after the collision with Orion C. So the final velocity is going to be the velocity of C plus the change in velocity. Sorry, that's not velocity of C, that is initial velocity. I can't read my notes. So it's initial velocity of the system plus the change in velocity. So initial velocity of the system we found earlier was here, it's 0.09 meters per second. And then this is in the y direction. So in component form, this is going to be 0. We knew that there was no initial velocity of the whole system in the x direction. So it's 0 and then 0.09. Plus, now the change in velocity is something else entirely. Key thing to realize is that change in momentum is equal to the change in velocity divided by the, or sorry, it's not the change in velocity, or it's the change in velocity times the change in mass. And in this case, well, and this also equals the impulse. If that doesn't make sense, maybe this equation will. We have the impulse of the system. So we'll take that 143.3 and negative 25. And we're going to divide it by the mass of the system, which is A and B is 1,500 kilograms. If you do that up here, you'll see we get the exact same thing. Change in velocity is equal to impulse change in the mass. But in this case, we don't have a change in the mass. So the mass remains the same at 1,500 kilograms. This could also be written as just m up here, which it is in our case. Anyways, if you do this equation, and the way you do this for vector form is you take 143.3 divided by 1,500 and negative 25 divided by 1,500, and then you would add the y components and add the x components. You end up with x component is 0, so 0 plus 143.3 is just 143.3, divided by 1,500 is 0.096, and do the same for the y, and you get 0.073. So that's the final velocity in collision form, or sorry, component form. Question 3 asks us to calculate the angular impulse delivered to the Orion A-B system. So angular impulse, we'll call delta L. The equation for it is the average torque times the change in time. Remember that change in time was 0.05 we found earlier. So this is during the collision. Average torque is given by the force in the perpendicular direction times the r, which is the distance from the center of mass. If you read the equation earlier, you see that the r is equal to 1.5. But before I go through and try and solve this, I'm going to rearrange it a little bit. So let me do a little erasing, give myself a little more space. So we have that for torque, the force times r, the force in the perpendicular direction, times delta t. We can rearrange this though, because all of these are just multiplied together to be the force in the perpendicular direction times delta t times r. Now this one might look a little familiar to you. Force times delta t is just equal to the impulse in the perpendicular direction. You can see that from here if you were to rearrange this. So we just have impulse times r. And since we know that it is a perfectly elastic collision at, in the x direction, it's just 143.3 times 1.5, which is our r. If you plug that into the calculator, you get 214.95. And then this is Newton meters. Yeah, Newton meters. Okay. Question 4 asks us to calculate the final angular velocity of the Orion AB system. Key thing to realize is that delta L, which is our angular impulse, let me section this off real quick. Easier to see. Delta L is equal to I times omega. That's just a fundamental equation, which means that omega is equal to delta L angular impulse divided by I. And we're given I up here. I of the AB system is 4,500 kilogram meters squared, which means that omega is going to be 214.95 divided by that 4,500. And if you plug this into the calculator, you get 0.048. And then this would be radians per second. Final question asks us in 1 or 2 sentences, describe the complete final motion of the Orion AB platform. What is the center of mass doing, and what is the platform itself doing? So we know that from this, with our final velocity, it has a final velocity in the positive x and positive y direction. So I'm going to say that this is our AB system. So it has a velocity kind of in this direction, positive x and positive y. We also know that, well, that's what the center of mass is doing, is what I should say. The center of mass is moving, it's translating linearly along that direction with that velocity. And then the platform itself is rotating about the center of mass with a constant angular velocity of 0.048 radians per second. And then it's moving, let's see, does it give us which direction? This is R is 1.45 meters below the center of mass. So if you imagine that here is AB and here is C approaching here, this is going to cause this to rotate this direction, so counterclockwise. So that's the direction it's rotating and the full description of what's happening. The platform itself is rotating counterclockwise at 0.048 radians per second, and it's moving in the positive x and positive y direction described by this velocity. But that's the end of this video. If you liked it, as always, I appreciate a like or a subscribe. And as always, thanks to Krish Kotak for making this problem set for us.